Chapter 4 ultimately deals with situations where we've got two variables at a time, two quantitative variables. So instead of just one measurement for every individual, we have two. And essentially the way that it works is if you have two quantitative variables measured for every individual in a data set, then if you want to graph that, you put one on the x-axis, like how we have living area in square feet, definitely a quantitative variable. We got that on the x-axis. We got price on the y-axis, also definitely a quantitative variable. And if you graph that, then every individual is a point in the scatter plot. So this one right here, I guess that's about 4,000 square feet, costs a little less than $800,000, right? So that's one house right there. Or then this one right here, living area, I guess that's, I don't know, maybe $1,750 if I had to guess. Price is real low, right? So maybe that's a house that's been gutted. That's why the price is so low, something like that. So that's how it would work. Every individual would be represented by a point in the scatter plot where that point is just plotted like an ordered pair, right? X measurement, Y measurement, that kind of thing. And then what can you see in the scatter plot? So why would you make one? Well, you could look for associations between the variables, any kind of trends that you might see in the scatter plot. So the things to look for, like it says in this last sentence here, direction, form, strength, and outliers, and we're going to go through those one by one. Direction works essentially the way that slope works, like in algebra. So the first one about having a positive association or a positive direction in the scatter plot, that's, like it says there, lower left to upper right. So that means that small values of one variable go along with small values of the other. Large values of one variable go along with large values of the other. But then if you think about, like, what does a line with a positive slope look like? Well, if you go left to right, the line goes up, right? If you have a line with a slope of 2, that's what it looks like, right? So that's what it does. And that's the idea, right? So it works the way that slope works in algebra. The negative association or negative direction in the scatter plot, that's large values of one variable with small values of the other. And so if you go left to right, the scatter plot would kind of drift downward. And that's how a line with a negative slope works, right? If you have a line with a slope of -3, then you go left to right, the line goes down. So it's that exact concept just applied to something that's not linear, right? I mean, it's a scatter plot. You got a whole bunch of points, not just a line. But it's the same concept. Form, I'm going to scroll down a little bit here. Form is basically going to be, is it linear or is it curved? If the overall pattern looks relatively linear, it doesn't have to look like a perfect straight line, but like if you were going to draw in sort of a best fit curve, so to speak, and it ended up being a straight line, that's a linear enough pattern. And one that's curved would be one that had a clear arc to it. You do see that. You do see situations where the scatter plot obviously has a kind of arc. Then the stuff that we're going to do later in this section where we make linear models, that might not fit so well, because if you're making a linear model, you would think that fits with a linear shape, and that pretty much is the way that that goes. Strength. Strength is basically how obvious is the pattern. How much does, if it's a linear shape, how much does that scatter plot kind of like wrap around the line? Like, does it look really linear, or is it just kind of linear, or, that kind of thing? And there is a way to actually measure strength, which we will get to. There's a way to quantify it. So then that way you don't have to eyeball it, right? Because not everybody is going to see the same thing necessarily. And then, are there any outliers? Okay, so this is actually worth describing a little bit, and that's why I made these little pictures over here. That an outlier has to be outside the overall pattern, but because this has two dimensions now, right, because you got one variable on the x-axis and another one on the y, you can have a gap and still have a point that's not an outlier, which is what this scatter plot on the left is supposed to illustrate. That green dot, there is a gap between where that is and then where all these blue ones are, right? There's no argument there. There's a gap in here. But it's still within the overall pattern, right? It looks like if you made a best fit line, it just kind of goes through all these blue points, and it ends up kind of over here by the green one. And you go, okay, fine. That's not that weird. It's just, the X variable is a lot bigger, the Y variable is smaller, but it still fits the pattern. That's ultimately not an outlier, even though there's that gap. However, the other scatter plot over here with the red dot, that's definitely an outlier, because if you kind of imagine with these blue dots over here, if you made a best fit line for those blue dots, I mean, certainly it's a line, right? This is linear. But if you did a best fit line through the blue dots, it's just going to go right through here, right? And that red dot up in the upper left is nowhere near that. So that point is really weird compared to the other ones in the scatter plot, because for an X value that small, it seems like the Y value should be a lot smaller to fit in with the overall pattern, right? You got a little X value and a giant Y value, and that's not the kind of thing that goes on when you have a positive association like this. Or I guess you could say, like, well, for a Y value that's that big, then the X value should be a lot bigger. I guess you could look at it from that perspective as well. Either way, that's way outside the overall pattern. That one's an outlier. The next page, we've got an example, and I think I'm going to have to scroll up and down a lot for this part. Either that or make this really small, so I figured scrolling up and down is the lesser of two evils. And what we've got is a data set of hard drive capacity versus cost. So the thing that you probably anticipate is like, well, if you have a hard drive with a higher capacity, that probably costs more money. And that does generally appear to be the case. If you go left to right, those points do seem to go upward. So that is the first part of this. What about the direction of association? It looks positive because as one variable goes up, the other one goes up. So I think we can put that in here, that there is a positive association. And I suppose we can make this a little more specific with the actual variables. So something like price increases as capacity increases. So price increases as capacity increases. I think that's about as economical as I can write that, right, with as few words as I can. But sure, I mean, you look at this thing, yeah, the points, they generally go upward from left to right, especially once you start getting into the, above 5 terabytes here, right? Then that's definitely what's going on. These down here, like, they're not nearly as big, and, maybe there's like a slight increase down there, but then once we get out here, it's like, oh yeah, I see the trend. But then the next question is, what about the form? So is that linear or is that curved? And this is where I think it helps to just kind of mentally try to picture, what would a best fit curve to that thing look like? Is that going to be a straight line? I would argue that it's not. It almost looks more like a parabola, right? Because it kind of goes through those and then kind of gets steeper, right? Right? There's some arc to this, it looks like. So I would say that this is not linear. It looks like it's curved upward. So that's what I'm going to put in here, that this is curved upward and not linear. And then the next question is about strength. So what can we say about the strength? Well, if we go back up to where it is, it looks like if you're going to put in a best fit curve, it's pretty clear where it goes. And that, in a way, is kind of a way that you can estimate how strong the relationship is. Like, if you could kind of look at it and think, if I drew it, I know just about exactly where I'd have to put it, then that's pretty strong, right? If the scatter plot is a little more haphazard looking and you can't do that, or if you think, well, it kind of goes through here, then that's a weaker relationship. But here, we can see pretty much where it would have to go if you put in that best fit curve. So that's a pretty strong relationship. So that's the kind of thing I'm going to write in for part C. So something like the points appear to be clustered along the curve. curve, not curved. There we go. And so that means that there is a strong pattern, right? We can see that just looking at the scatter plot. It looks like there's a strong pattern there. And that means that you have a strong relationship between the variables. Okay, next, do we have any outliers? If I scroll back up, there is one point that's pretty far away from the others, but it's not outside the pattern, right? If you draw in that arc, it looks like the arc pretty much goes right to it. So there's a big gap in here. We don't have any hard drives with a capacity between, I guess that looks like it's about 12, and then that one's like 32. So there is a pretty big gap in here. So it's farther away from those other points, but it's still within the pattern, so we're still good, and that is not going to be an outlier. So this is that exact situation where I think it's easy to look at it and kind of go, okay, gap equals outlier, but with two separate variables being graphed with a two-dimensional graph instead of just a single variable, then if you have that gap, that's not necessarily an outlier, and that's kind of where we are right now. So does the scatter plot show any outliers? We are saying no, that the 32 terabyte drive is positioned far away from the other points. But it still fits the overall pattern. So, but it still fits into the overall pattern. Section 4.2 is pretty short. There's one idea in it, and that idea is, so you have two variables that you're measuring. Does it matter which one goes on the x-axis and which one goes on the y-axis? And the answer really is it depends. If you have some idea of, like, you think that there might be a cause and effect relationship between the variables just based on what those variables are, like if you think, okay, if I change this one, that's going to force this other one to change, then you want to put the cause variable, which is your explanatory variable, on the x-axis, and then the effect, which would be the response variable, on the y-axis, right? So then that way, when we get to making the regression models, they end up being functions of y, or functions of x rather, right? So y equals f of x, that kind of thing. So then the input is x, the output is y. So if you have this cause and effect idea, then it makes sense for the cause to be the input and the effect to be the output. The other side of that is that when we get to the models later, you can still make a model if you don't really have like a cause and effect idea. It'll still work for prediction, and in that case, there's probably something else at work that you have to kind of account for, but I guess we'll get to that part later when we get to it. So the example that's here, with the disk drives, we had capacity on the x-axis and we had price on the y-axis because it would make sense that if you have a hard drive with a higher capacity, that would cost more money. And it seems like that's the way that would work, not the other way around. Right? Not that if price goes up, that would make the capacity go up. That's not going to be the way that this works. It's going to be if the capacity goes up, it makes the price go up. So that's why we would set it up this way. So we'll say that if there is a cause and effect relationship here, which it seems like there should be, but I'm going to write this as though we're hedging our bets slightly. So if there is a cause and effect relationship here, it's going to be that the larger capacity causes an increase in price. So it's going to be that a larger capacity causes an increase in price. And that's it for section 4.2. 4.3. So I did briefly say in passing earlier that you can quantify strength. This is the way that you do it. This thing called the linear correlation coefficient, which most people just call the correlation, denoted by R rather than C, right? C is kind of reserved for an arbitrary constant mathematically, so I had to go with something else. So it's R. That is the most common measure of strength of a linear relationship. So there's also a longer name. Most people just say the correlation, like how I have it written here. The correlation describes the direction and strength of a straight line relationship between two quantitative variables. You can grind it out by hand using z-scores. That's what those are. So the zx and the zy are z-scores. Basically what you would have to do is each individual would give you two z-scores, right? You'd get a z-score for the x measurement and one for the y measurement, since you have two measurements for each individual. So you'd have to do that. You have to get all those z-scores. For each individual, you got to multiply them together. And then you add up all those products, and you divide by n minus 1. So yes, you could grind this out by hand, but I think at this point in time, this is one of those things where we would say that's what the calculator is for, or that's what the software is for, and kind of leave it there. And we'll just worry about how to actually interpret the value that we get. So the direction part, you think, well, do I need the correlation for that? Because if I had the scatter plot in front of me, I can figure out if it's positive or negative. That part's not that difficult. That's true, but if maybe you didn't have the scatter plot in front of you, then that would be helpful, right? So that's where that comes into play. You kind of get the direction for free, even though if you have the scatter plot, admittedly, you probably don't need that part. The part that you do need is strength. So that's really what this is for. And we are going to do one of these by hand, sort of, but not really. And really, we're just going to do the first individual here, the little one. What this is, I happen to know this off the top of my head because this is kind of a classic example. It's Archaeopteryx bones. So there aren't a lot of those, right? Like there aren't a lot of those fossils. That's why we only got 5 Archaeopteryx here. And the reason that there's one that's way over here in the corner is because that one isn't full grown. Right? I don't know if it's a baby, but I mean, if you think, okay, these up here are the adults, one of them is really big, right? Even compared, like the other 3 adults are kind of around the same size, but it looks like this is a big one here. That must be like the firstborn Archaeopteryx, maybe. And then this one is definitely smaller, but it still fits the overall pattern, right? So smaller humerus, smaller femur. So, okay, fine. That's the same animal, right? It's the same prehistoric bird, just a smaller version. So probably a younger version. So not that weird, right? That a younger version, right? Maybe one that hasn't grown to its full size, then both bones are going to be smaller. All right. So then the means and standard deviations are up here, and we really just need those one time because the other boxes are all filled in here. So for that first Archaeopteryx, the small one, so the z-score for x, which is the femur, so we would have 38 minus 58.2 over 13.2 for the standard deviation, right? So this is just a z-score, right? You got your observed value, the 38, right? The length of the femur minus the mean and then divided by the standard deviation, and you get negative 1.530. And then with the humerus, I guess just make sure that we're using the right mean and standard deviation now. So here it's going to be 41 minus 66 over 15.89. And that's going to be negative 1.573. And this is by far the largest product of z-scores that we're going to get because these two are pretty far away from the zero. You get about 2.5, I would think, maybe a little less. Yeah, 2.407. That makes sense. That checks out. And there we go. And then from there, we could grind out the correlation basically just by adding up those products. So we can do that, and I'll just write all this out and then point at the final answer in a second. I went ahead and wrote in a couple other things too besides the correlation. So you would add up all those products of the z-scores, and then you divide by the sample size minus 1. Ultimately, you get 0.994, which indicates a very strong correlation. If you're getting a perfect linear shape with a positive association, you would get exactly 1. You can't actually go higher than that, which is one of the correlation properties on the next page. So this is actually really strong, but then when you look at what the scatter plot was like, you think, well, yeah, sure, that looked pretty linear. But then the other stuff I wanted to put in here was how you would get this without grinding it out by hand. So this is how you do it with the calculator. The diagnostic on may already be set up that way, but if it's not, then it's not going to work. So if you go into the catalog, you can do it. And I'll run through that in a second. Then enter the data, probably in L1 and L2, but just kind of wherever, I guess wherever you got open columns, that's where you're going to put the data, presumably. And then there are a couple of linear regression options in the calc menu. Either of those will give you the right correlation. So the difference between the two is how they give you the linear model, which we're not quite there yet, but we will be shortly. So the calculator, I do have the emulator open here, and I think even with the smaller window, I can still get all this in. So let's see, then here the diagnostic on thing first. So second, and then catalog, which is the secondary function of 0. And if I go down to where the D's are, and this does not want to do that, does it? There we go. And diagnostic, there we go, diagnostic on. So that's taken care of. And then you'd want to go to where your lists are. Let's see, I don't want that one. So I guess I've got L5 and L6 here, but that's fine. So 38, 56, 59, 64, and 74. And then for the humerus, 41, 63, 70, 72, and 84. Okay. And then second and quit to get out of there. And then I said the fourth one. The eighth one will also work. And you can see what I mean, like AX plus B, A plus BX. That's the difference between those. It's does it give you the slope first or the intercept first? But we are not quite up to the modeling yet. So I will put that in there. My X list, let's see, I had L5 and L6, right? So second L5, Y list, second L6. And then if we calculate, there's the correlation right on the bottom, right? The R, we said that was going to be the symbol for correlation. There's the 0.994, right? Just like we had with the one with all the algebra. Got the same number. All right, so then going back here, you could also do this in Excel. So if you're going to use Excel, the data analysis tab will do it, and there are a couple of options that will give you the correlation. Regression will give you more than just the correlation, but it will throw that in along with a bunch of other stuff. Correlation will pretty much just give you the correlation. So I can show you what happens here. If we go to Excel, I've already got the data in here. And so then what I'm going to do, and I know this is cut off, but data up here, and then I want the data analysis tab, that's not cut off. And then correlation, and then select my data, and then OK, and I'll just let it go into the new worksheet. There it is. So it gives you this 2x2 table. The ones you can kind of ignore. The ones are just the correlation of femur with femur and the correlation of humerus with humerus. Those really aren't interesting, right? Any variable's correlation with itself ought to be perfect, right? Like that's not anything that's of interest ever. The one that matters is the 0.994, right? And that's the correlation between column 1 and column 2. So between femur and humerus. So there's that. The other way to do it, I said it was to use the regression option. So if I scroll down to it, we can go there and input Y range. I guess Y can be the humerus and X can be the femur. There's no cause and effect relationship here, right? The variable that really makes both of those increase would just be the Archaeopteryx gets older, right? It gets older and it generally gets bigger, so the humerus gets longer and the femur gets longer. But you get a lot of extra output. The correlation shows up, and I'm just going to stretch this a little bit. Where it says multiple R, that's where the correlation is, right? You can see the number, you go, okay, sure, the 0.994, I remember that one. Yeah, that's where it shows up. A lot of other stuff shows up too. We will need some of these things later, but not all. So if you're looking at this and thinking, I have no idea what all these things are, we won't need too many of them. A lot of them are in part 2 of chapter 4, like the ones that we're going to need. Kind of eyeballing this, I think we actually only need 3 other numbers besides the correlation. There are only 3 other things that we actually need here. So it looks more intimidating than it is. The last stuff on this page, the biggest part I think is actually right here, the word that's in bold, which I suppose would be logical that would be important. But the correlation does only measure the strength of a linear association. So if you have a different shape, then you may have a strong pattern, but if it's not linear, the correlation might come back saying that it looks like a weak linear association. The classic example of that is if you have like average temperature, like average daily temperature for several years, where then basically what happens is it just keeps going up and down, right? You get up, right, the higher numbers in the summer, you get the lower numbers in the winter, and that just kind of repeats over and over again. Kind of like a sine wave shape almost, and that's non-linear, so like applying the correlation to that kind of shape just doesn't work very well. So okay, stuff that we need for the idea of correlation to make sense, you have to have 2 quantitative variables, right? Pretty clearly we couldn't do the computations if one of the variables was not numeric, so okay. Yeah, we need that for sure. Then you do need to have something that looks pretty straight in the scatter plot. Doesn't have to be perfect, but you do want that to generally be the overall pattern. And then if there are outliers, the accepted convention is kind of, well, try it with the outlier, try it without the outlier, and kind of report both. And that's usually the way that that's handled. Correlation properties. There are quite a few of those, and some of them are more important than others as far as this is how the correlation works, but they're worth running through. So the sign does give the direction of the association. Again, like before, if you had the scatter plot, you probably don't need that part of it, but if you didn't have it, then it would be nice to see, oh, it's a positive correlation. There's a positive association here. The way that it's computed, it has to be between -1 and 1. In theory, you could get exactly -1 or exactly 1, but not in practice. I mean, in order to get a 1 or a -1, you have to get a perfect straight line, and the real world is a little bit messier than that, so you don't really see that in real life a whole lot. Next, the order of the variables doesn't matter. No, it doesn't, because in the formula where we went through it algebraically, where we had zx times zy, if you flip the order of zx and zy, you're going to get the same thing, because multiplication commutes, right? 3 times 2 and 2 times 3 are both going to be 6. It's basically that idea, just applied to correlation. No units, because z-scores don't have any units either, because when you divide by the standard deviation when you're computing a z-score, the units divide out. So if the z-scores don't have any units and the correlation is made of z-scores, that doesn't have any units either. Let's see. You can change the scaling, which is good, right? So that means like if you have length measurements, like a femur or a humerus or something, those are measured in centimeters, but if you switched it to imperial measure and did it in inches, you would get exactly the same correlation. So that's good. Use a different measurement system. Correlation does not get messed up by that. Linear association specifically. Okay, we did talk about that. Sensitive to unusual observations like outliers. Sure, because z-scores are computed with the mean and standard deviation, and those are sensitive to extreme observations. So, therefore, the correlation is too. Let's see, only makes sense for quantitative variables. That is true. Doesn't imply causation. Right? Just because you have a strong correlation, that doesn't necessarily mean that a change in one variable causes a change in the other. I think the humerus and the femur is actually a good example of that, right? Because really it's not that one of those getting larger causes the other bone to get larger. It's more just the Archaeopteryx gets older and it grows, like it generally gets bigger, so then both bones are getting larger. It's more like that. So really the cause is not one of the two variables being measured. And then the correlation of 0 doesn't imply that there's no relationship necessarily. You might have a relationship, just not a linear one. So that's why I made a little sine wave here, because the correlation of that is actually going to be pretty close to 0. And you look at it and you go, well, the pattern's really obvious, and it is, but it's not a straight line. Right? And if the correlation is supposed to measure the strength of a linear relationship, there's not much of a linear relationship there. So you don't really end up with much of a value of the correlation. It'll be close to 0. So let's see. The big ones here, that's a big one. Let's see. That's a big one. I would say this is kind of a big one at the bottom, but we're not going to get too deep into the transformations and things, because that's what you do if you have a nonlinear shape. Maybe if we were having class in a computer lab or something, then maybe we would have that showing up. I think this is important, right? That the correlation is always between -1 and +1. And basically the way it works is values of the correlation that are close to 0 are pretty weak. And the farther away you get from 0 in either direction, that indicates a stronger correlation. So like a -0.9 is pretty strong. That's pretty far away from 0, considering you can only go out to -1, right? So something like a -0.91, -0.86, like those are actually pretty strong. But I think those 3 that I have starred, those are probably the 3 biggest ones there. Let's see. Then the table. Okay, we kind of saw one of these, just smaller, because there was one in Excel, right, where it had the 2 1s and then it had the 0.994 in the corner that we were actually looking for. But this is with a whole bunch of variables. And notice that the correlation of the variable with itself is always going to be 1, right? It always matches up perfectly with itself, which you think, well, it would kind of have to, wouldn't it? It's the same measurements in both columns if it's just one variable with itself. So this is a correlation matrix where you can check the correlations between a bunch of different variables all at once. And then you can be like, oh, well, it looks like it's the age and lot size. That's pretty weak. That's really close to 0. Price and living area looks kind of strong, right? The 0.712, right? You go, that's a lot bigger than 0, considering you can only go up to 1. Let's see, a 0.59 between lot size and land value. That's pretty weak. Let's see, we don't really have a -1 that's very strong here. I guess the strongest is the -0.189, and that's of the negatives, and that's still not very strong. But you could have a strong -1. We're just not seeing it in this particular example. The next section is about lurking variables, and this actually goes along with the Archaeopteryx too, because with the femur and the humerus, we had the strong correlation, really strong, right? 0.994, very close to 1. But it's not like the humerus being longer makes the femur get longer or vice versa. It was that the Archaeopteryx gets older, so generally it gets bigger, both of those bones get longer, right? And so the lurking variable there is the age of the Archaeopteryx, right? That's not part of the study, but it's the cause of why these other variables are changing. So what a lurking variable is generally is it's one that affects the variables in your study. But it's one that is outside of your study. It's not one of those two that you're measuring. So this example is another one that's supposed to illustrate this idea. So a study finds that during blizzards, online sales are highly associated with the number of snowplows on the road. So the more snowplows there are, the more online purchases there are. So the director of an association of online merchants suggests that the organization should encourage municipalities to send out more snowplows when it snows because he says that will increase business. Okay, this seems a little bit of an absurd concept that that's the driver, right? And that's where you go, okay, this looks weird. There's a lurking variable that is kind of driving both of those things. It's driving, more online shopping and more snowplows, because it's certainly not the case that there's a cause and effect relationship, right? It's not that you put out more snowplows that's going to make more people buy things online. The other way around also certainly doesn't work, right? If more people are buying things online, that doesn't make the snowplows come out. Okay, that no cause and effect relationship between those two things. There is a lurking variable, which is how severe the blizzard is, which that you could measure, right? You could do it as a quantitative variable. You could do it in the number of inches of snow, right? That's an easy way to get a blizzard to be a quantitative variable. And you go, okay, well, that could drive both of these things. The more severe a blizzard is, the more snowplows are going to be out, right? Certainly, it's a driver for that. But I think also, I scroll down a little bit, with adverse weather, and the more adverse it is, I think the more motivated people would be to shop online rather than going out to a brick and mortar store. Right? If you look out the window and it looks pretty rough out there, that's when you think, you know what? Maybe I don't really have to go out there. Maybe I could just do it from here. I won't get whatever it is that I want right away, but if this is the trade-off, I don't have to go out into that hideous looking weather, but I get to get the stuff that I want 2 days later. I think I'm okay with that. Right? That seems like a good motivator for shopping online instead of going out to a store. If the weather is terrible, and you say, well, I don't have to go out there. So the lurking variable here would be how severe the blizzard is, and that's going to be the driver for the number of snowplows, but also probably the amount of online sales, or I guess maybe the proportion of online sales versus brick and mortar sales, that kind of thing. The last part of part 1 of the notes, the last section, is really kind of foreshadowing what happens next more than anything else. Because the back half of chapter 4 is going to be about linear modeling. So this is foreshadowing here more than anything else. But it is kind of what you would expect it to be. It's the idea of a best fit line. So that's why the scatter plot's coming back that we had on the first page. And we had that correlation of 0.712. It's in the that correlation table where that 0.712 is coming from, but that's what it is. And you go, okay, it's positive, which we can also see in the scatter plot pretty clearly that we have a positive association here. And it's fairly strong, right? It's not super strong. It doesn't look perfectly like a straight line, but that's okay. Right? It doesn't have to be that. This is real life. Things do not, end up working out to perfection all the time. And so we want to get a linear model. So a linear model is just a linear equation. That's what it's going to look like. And the points on the scatter plot aren't all going to line up perfectly, which means that when we make the linear model, Not every point is going to be right on it, and that's all right. I mean, even from here, you can kind of see it. If you drew a best fit line through the scatter plot, it's going to go through this dense part of it, right? That's kind of what you'd expect. And there are going to be points that don't touch the line, and that's totally fine, right? It's just to summarize the relationship. It doesn't have to hit every single point. It's certainly okay if that doesn't happen. And then this is kind of going along with that idea. So what residuals are? So residuals are basically the vertical distance between where a point is and where the line is. So the linear model gets written like this, and we'll see a lot of this in the back half of chapter 4. So this y hat equals b0 plus b1x. So b1 is the slope, right? Like in the linear equation, the number multiplied by x is the slope. And really, when we get these, when we get specific ones, b0 and b1 are going to be some numbers, right? Maybe it's, 13.26 plus, 4.19x. And you go, okay, 4.19 multiplied by the x, that's your slope. That kind of thing. And then y hat, the value that you get when you substitute in a number for x, that's your predicted value for whatever that x value is that you subbed in. And in most cases, that will not match up with the observed value for an x value that's in your data set. So you'll have points that are above the line and below the line, is basically what that's saying. And you go, well, sure, I can see that in that scatter plot up in the corner on this page. Is if I drew in the line, there are going to be some points above it and some points below it. And then the residual, which sometimes is called an error instead of a residual. That's why an E is being used. And you think, well, we couldn't have used R because we used R for the correlation, so we got to use something else. And it's because the term error is sometimes used instead of residual that you can use an E. And so it's the observed Y minus the predicted Y to get the residuals. They actually show up in Excel if you want Excel to compute them. I didn't turn that on when we did the regression in Excel, but you can do it. It's not that hard to get them. And we'll see that when we get into the second half of chapter 4. And then the idea of the best fit line. So you can't really just add up all the residuals to see how well the line fits the data, because for every data set and every linear model, if you add up the residuals, you will always get 0. So, okay, well, if you get 0 all the time, you can't differentiate anything. So that doesn't work so well. The thing that you look at instead is the sum of the squares of the residuals, and the best fit line is the one for which that sum of the squared residuals is as small as possible, so it's minimized. And that's where you see the term least squares. So, like, least squares regression line. You'll see that if something's written up kind of formally. And least squares just means that the sum of the squared residuals is minimized, so therefore that is the line that fits this data set the best. That's really all that that's getting at. It's least squares regression line essentially means best fit line. And that, I think, will do it for part 1 of chapter 4.